everyone, welcome to my channel Simplified Organic. This is the first lecture of optical isomerism, and in this I'm going to discuss about three topics or three parts. That is, what is optical activity, what are optically active compounds, and what are the conditions for optical activity. Okay, so let's begin. For example, if there is a solution of an organic compound and a plane polarized light is passed through this solution. If a plane polarized light, also called as monochromatic light, when this PPL is passed through a solution, three conditions are possible, or three results I can say. One, there is no effect on PPL. The solution is not showing any effect on the PPL. Those type of solutions are called as optically inactive. Those type of solutions are called as optically inactive solutions. And if there is some effect, means it is rotating, if the solution is rotating the PPL, then those type of solutions are called as optically active solutions. Now this optically active, what exactly is this rotation of PPL and all this? We'll discuss later. For now, what you need to remember is there are two types of solutions in nature. One is optically active and the other one is optically inactive. The one which rotate the PPL, plane polarized light, are optically active, and the one which cannot rotate or do not show any effect on the PPL are optically inactive solutions. Now further, optically active solutions are classified in two types. Optically active are further classified in two types. One is dextrorotatory, and the second one is levorotatory. Dextrorotatory also represented as small d or plus, and levorotatory represented as minus or small l. Now, what do you mean by dextrorotatory? If the solution rotate PPL to right side, or clockwise, in this direction, it is called as dextrorotatory. If the optically active solution rotate PPL to the left side or anti-clockwise, are called levorotatory solutions. So overall, I can classify solutions in three types. First one is optically inactive. Second one is optically active, which is further classified in two types, that is dextro and levo. Dextro means the one which rotate the PPL to right side or clockwise are called as dextrorotatory, And LEVO means, and the one which rotates PPL on the left side or anti-clockwise are called as LEVO rotatory. Dextro are represented by small d and plus, and LEVO are represented by small l and minus. So overall, there are three types of solutions or compounds. Okay. So now the point here is, if I give you now, the first question is, this is the answer for the first question. That is, what is optically activity? This phenomenon of rotating the PPL either to the right side or the left side is called optical activity. This phenomenon, the phenomenon of rotating PPL either to right side or left side, means dextro or levo, is called optical activity. Optical activity. And the compound is said to be, and the compound is said to be optically active. The compound is said to be optically active compound. So this is the answer for the first question. Now coming to the second one. If I give you a solution, you can easily identify whether the compound is optically active or not by just going through the experiment, by using polarimeter. What is polarimeter? The apparatus used for this experiment. The apparatus used for or to check optical activity. To check optical activity. Okay. So if I give you a solution, you can easily identify whether the compound is optically active or not by using this polarimeter. Now the second point is here, what if I give you a formula? What if I give you IUPAC name of a compound? Like for example, if I ask you 2-butanol, is it optically active or not? So how can we identify by looking at a compound? Or if I give you a IUPAC name, how can you identify whether the compound is optically active or not? So for that, you need to go for some, you need to follow some conditions. So now the point is conditions for optical isomerism or conditions to be optically active. Conditions for optically active. Optically active compounds are also called as chiral compounds. Optically active compounds are also called as chiral, CHIRAL. So what are the conditions to be chiral or to be optically active? What are the conditions? So condition number 1, there should be a chiral center. There should be a chiral center. What do you mean by chiral center now? What do you mean by chiral center? Chiral center means an atom bonded to different atoms. An atom bonded to different atoms is called as chiral center. Like for example, I have an atom at the center, and this have 4 bonds, and it is bonded to 4 different groups or atoms, A, B, C, D, bonded to groups or atoms. So there are 4 different groups, A, B, C, D. Therefore, this center is chiral center. This is called as chiral center. Generally, if you take carbon, it's called as chiral carbon. Like for example, I have this type of compound, something like this. So now look at this center carbon. This center carbon is chiral carbon because it is bonded to 4 different atoms or 4 different groups: methyl, aldehyde, alcohol, hydrogen. So this carbon is called as chiral carbon. Like one more example. If I take this fluorine, chlorine, bromine, iodine. Now this carbon is bonded to 4 different atoms: fluorine, chlorine, bromine, iodine. Therefore, this carbon is chiral carbon. So, what do you mean by chiral center? Or if it is chiral carbon, you call it as chiral carbon. If it is bonded to 4 different atoms or 4 different groups, it is called as chiral. Okay. Now, coming to second condition. There should be no element of symmetry. There should be no element of symmetry. Now, what do you mean by element of symmetry? Element of symmetry are of 3 types. First one, plane of symmetry. Plane of symmetry represented as POS. Plane of symmetry. Second one, center of symmetry. Center of symmetry represented as COS. And the third one, axis of symmetry. Axis of symmetry called as AOS. These are 3 elements of symmetry, and the point is this should not be present. There should be no element of symmetry. Now, mainly I'll discuss about plane of symmetry and center of symmetry. These are important. So, what is plane of symmetry? What is plane of symmetry? Plane of symmetry. It is nothing but an imaginary plane which bisect the molecule into 2 equal halves. 2 equal halves or 2 equal mirror images. So an imaginary plane which cuts the molecule into 2 equal halves. That is called as plane of symmetry. Like for example, if I take cis 1,2 dimethyl cyclopropane. So if I draw the structure, it will be like this. This is a cyclopropane, and cis means both the methyls on the same side. So this is a cis 1,2 dimethyl cyclopropane. So I can cut this molecule into exactly 2 halves by passing a plane, an imaginary plane. So this is the plane of symmetry. So this molecule have plane of symmetry. Okay. This molecule have plane of symmetry. One more example we can take for better understanding. It is cis 1,2 dimethyl cyclobutane. 1,2 dimethyl cyclobutane. So this is the cyclobutane. and two methyl groups. I'll take another color. These are the two methyl groups above the plane as they are cis. Cis means on the same side, right? So I can cut this molecule into exactly half by passing a plane. So this is plane of symmetry. So this molecule have plane of symmetry. One more example, like cis 1,3 dimethyl cyclopentane. Now this is the cyclopentane, and these are the methyl groups. I'm calling it as cis because both are on the same side. And if I pass a plane through this, I can cut this molecule to exactly half. So therefore, this is called as plane of symmetry. So it's an imaginary plane if you through which you can using which you can cut the molecule to exactly two half is called as plane of symmetry. Okay. Now coming to the center of symmetry, second important element of symmetry, that is called as center of symmetry. What do you mean by center of symmetry? Maximum examples you can easily solve by using just plane of symmetry. Maximum examples you can see plane of symmetry. Now it's an imaginary center. It's an imaginary center of molecule. This is important. Imaginary center of molecule. This is very important. Imaginary center of molecule from which when you travel in opposite direction, when you travel in the opposite direction at same distance, we find same group. We find same group or atom. I'll explain this with an example, then you'll understand easily. Like for example, I have trans 1,3 dimethyl cyclobutane. This is the example I'm going to discuss. So this is the 1,3 dimethyl cyclobutane and trans, one methyl above the plane, one methyl below the plane. And when you travel from the center, this is the center of the molecule. And once again, I'm repeating, it should be center of molecule. It should be center of molecule. So when you travel from this direction, in opposite direction, one above the plane and one below the plane. When you travel in the opposite direction, at same distance, you will get same groups. See, I'm getting the methyl here and methyl here. From the center, both the methyls are at the same distance, but in the opposite direction. Okay. So this is called as center of symmetry. Called as center of symmetry. One more example I'll discuss. One more example, that is trans 1,4 dimethyl cyclohexane. Cyclohexane, the structure is like this. This is the cyclohexane. And 1,4 trans. This is 1 and this is 4. Okay. And now take the center of this molecule. This is the center of the molecule. If I travel in this direction, I'll get methyl here. If I travel in this opposite direction, I'll get methyl here. So this center is called as center of symmetry. So using these two, you can easily solve. Axis of symmetry is not required. So for a compound to be optically active, the point to note, for a compound to be optically active, there should be a chiral center. There should be a chiral center and followed by no element of symmetry. Followed by no element of symmetry, then the compound is said to be optically active. So I'm writing it here. Final statement, finally. For a compound to be optically active, there should be a chiral carbon. There should be a chiral carbon and no element of symmetry. No element of symmetry. Then the compound is said to be optically active. Optically active compounds are also called as chiral compounds. Chiral. If I tell you a compound is chiral, it means it is optically active. And for optically inactive compounds are also called as achiral. If I use the term achiral, then it means the compound is optically inactive. So in this lecture we have seen what is meant by optical activity, how many types of compounds are there, and what are the conditions for to show optical activity. Okay, so that's all for today. In the next lecture, I'm going to discuss further topics of optical isomerism. Thank you very much. Bye bye. Take care.